at Meta, where I was working on the reinforcement learning library of PyTorch, and basically looking into multi-agent learning in this library. Okay, so yeah, to start off, just an overview of 3 of the components that I'm going to talk about today. And basically, these components touch upon different parts of what people need to do multi-agent reinforcement learning. And first of all, I'm going to discuss a little bit VMAS, which is a simulator. Of course, for reinforcement learning, it's quite different from traditional supervised learning, where you need actually an environment where you collect your data and then a training loop. So VMAS takes care of the simulation part, where we want an environment where our agent can interact. Then I'm going to talk a little bit about what is TorchRL, and this is basically the official PyTorch reinforcement learning library. And then I'm going to talk about a last component that I developed at the end of my internship, which is a library which has a focused standardization in the field of benchmarking multi-agent reinforcement learning. And this library basically takes all the components together from simulation and training into one suite that allows you to easily perform training. So here is a little bit of the agenda of like 4 main sections that we're going to see today. First, I'm just going to give a very brief overview of what was our interest, research interest in multi-agent reinforcement learning. Then I'm going to talk about simulation and learning. For simulation, we're going to see the example of the VMAS simulator, and then for learning, we're going to dive into TorchRL. And then I'm going to give a brief look at BenchMARL and the feature that it has. So for the motivation part. So as some of you may know, in the ProRock lab, basically we study multi-agent and multi-robot systems. And one of our missions is that of achieving collective intelligence in these systems. And we know that collective intelligence is kind of commonplace in natural systems. And this is intelligence where like, it's not just the sum of the parts of the intelligence of the members of the system, but it's actually something more, some added value due to cooperation. And what our mission is to have this kind of intelligence basically in robotic systems, and how can we achieve it or even improve it upon nature's work. And so why do we look into robot learning as a mean towards this end of reaching collective intelligence? And well, one of the main reasons is that the centralized sequential decision-making, it can be extremely hard. Like, for example, here on the right, you can see a multi-robot path planning task, where there was a talk also in the Wednesday seminar last week about these kind of problems, where the complexity of this problem, where the agents need to reach their destination without colliding with each other, grows exponentially in the number of agents. And so it's very hard and very computationally expensive to solve bigger and bigger instances of this problem. So we can think of using exact methods to solve these kind of things, and these methods grants us optimal solution, but they have a complexity that scales in the number of agents. On the other hand, we can think of meta-heuristics, which basically lack these optimality guarantees of such methods, but have better computational complexity. And as I see it, multi-agent reinforcement learning can provide a solution which is in the middle between these two, where it's able to approximate optimal policies via training. And basically what we can do is that we can train our agents on smaller instances of this problem and efficiently generalize to bigger instances with more agents. So these are some examples of works that we did in our lab relating to these kind of problems. In the first one, you can see a team of robots. These are ground robots that are trying to navigate towards a gap in a wall, and they're doing so using a policy that was trained using reinforcement learning in simulation, and they're communicating with each other. And this kind of work was analyzing the difference in the sim-to-real gap that had to be addressed in order to deploy this communication policy in the real world. And basically, this work shows that this can be done with just training in simulation. This is another example of a centralized decision problem, where basically we are tackling a traffic scenario where multiple cars have to coordinate with each other in order to improve the overall system flow. And this is again hard because you need to kind of achieve the greater good and not only act based on the selfishness of each driver wanting to take the least travel time. And lastly, this is a recent work where basically we investigated the impact of heterogeneity in multi-agent reinforcement learning, and how this relates to resilience. In this case, was resilience to the sim-to-real gap. But yes, so these are just some example of like scenarios where we train in simulation and applied on real physical agents our research. But so what about this training part, this simulation part? How does it happen, and what can you use to simulate multi-agent reinforcement learning scenario inspired by robotics? So the first thing I want to talk about is this simulator called VMAS, which we worked on a year ago. And basically, this is a vectorized multi-agent simulator. It's open source, and it's designed for multi-agent reinforcement learning. It's comprised of mainly two components, a vectorized physics engine written in PyTorch, and a set of scenarios. Among its features, we have, of course, the first is vectorization. This means that the simulation is performed in a batch on a GPU. And basically, this way we can leverage the single instruction multiple data paradigm of GPU computation, and basically perform scaling the number of environments that we simulate at the same time without any computational increase in the time. Then we wanted it to be quite simple, because there are some full-feature physics engine out there which do a really good job, like Unity or Bullet or like that. But what we wanted from VMAS is that we would be able to achieve the right trade-off between complexity and speed in order to just focus on the high-level NP-hard part of these decision problems without caring so much about the detailed physics of the low level. And so we wanted something where complexity can be tuned. We also wanted it to be general, so it's structured so that you can implement your own problems in no time. And extensible, again, we want to have abstractions for the users to just plug in and just, without learning how everything works, just learn what they need to implement and write the few lines to define a scenario. It's customizable, so there are a lot of things that you can change. For example, physical quantities like gravity, friction, drag, shapes of the agents, masses, but then you have like also other decisions regarding communication between the agents, the sensors that they use. For example, we have LiDARs, and then there is much more. So there is modular sensor, modular dynamics. For now, we have like differential drive and holonomic. We also have joints where you can create different shapes by constraining physically using joints your agents, and controllers, for example, if you want to control your agents with velocities or forces, and so on. And so here is an overview of some of the scienarios that we have. As you can see, there are many already, and they are usually inspired. Some of them are inspired by biological tasks. For example, you can see flocking up there, where we basically want agents to flock together while avoiding obstacles. Then there are others inspired by games like football, where it's a higher level strategy game that the agents have to play. And then there is other scenarios, for example, like sampling, where the agents have to sample a latent distribution, and these can model problem relating to exploration versus exploitation trade-offs. And again, we have also other scenarios where the agents are physically linked with a joint, requiring like a high degree of cooperation because their motion now is entangled. But basically, yeah, creating each of these scenarios requires very little, and for some of these, it took less than an hour to code it. Once you kind of know how to do it, it's very easy to integrate your own. And one question that we often get, since this is for robotic, is well, it's very simple. So does it work in the real world? So for this, we did a few deployments where we showed how this can be deployed on the robots. And this is a simple policy that needs to track a trajectory of a circle. And here is deployed on a RoboMaster, the DJI holonomic robot. And this is another example, similar to the one I shown before, where basically we train this policy where one agent has to give way to the other in simulation, and then we deployed it in a counterpart scenario in the real world. Yes, and lastly, I wanted to talk about what does it mean for vectorization, so that this can lead us to the training part. Basically, to show the impact of vectorization, we compared this simulator with the normal MPE. MPE was a simulator that was introduced by OpenAI in the MADDPG paper, and it's basically run normally on CPU. So you can see that here we plot the number of environments versus time that it takes to simulate them. And you can see for when you run VMAS on the GPU, as long as your GPU has enough memory, there is not really time scaling in number of environments because we can leverage parallelization of GPU. And even on the CPU, we can see a greater benefit than just normal MPE on the CPU, which just scales linearly, as you would expect from a normal, let's say, for loop kind of thing. And so what we want from a training library, since we think that this paradigm of vectorizing your simulation is the future, what we want from the library is that it is able to actually take this paradigm and use it. So if we're performing our simulation on the GPU in a parallel fashion on a certain device, we might want to keep the data on that device, not have any transfer, and just stay on the GPU for the training. And so here we compare, it's a similar plot where instead of time we show frames per second, but basically we compared RLlib, which is another popular reinforcement learning framework, to TorchRL. And basically RLlib, not having support for vectorization, has a simple for loop in the number of vectorized environments, and this leads to the same frames per second in the scaling of the number of environments, while TorchRL can actually increase the frames per second as you increase the environments, and have arrived to something like 500,000 frames per second. And so this brings us to how we can use this simulator for learning and to TorchRL. And basically, before diving into multi-agent reinforcement learning in TorchRL, I just wanted to give an overview of what TorchRL is for those of you that are not familiar with it. It's quite a recent initiative. It's a few years, but it's acquiring traction quite rapidly. So TorchRL is the PyTorch reinforcement learning library for decision making also. It's a PyTorch initiative, so it comes with the quality standards, the guarantees of maintenance, and the effort of Meta, which is backing the project. It's aiming to be modular yet integrated. So what it provides is standalone components that you can use for reinforcement learning, for example, replay buffers, losses, environments. And you can decide to just use some of these components or use a full pipeline. But it should, the focus is that it should be easy to just use a part of it, like a data loader, for example, in the supervised domain. The syntax aims to be unsurprising to practitioners. It aims to have a breadth over depth functionality. And this was really useful for me because unlike other libraries like RLlib, it's quite easier to hack and to understand what is going on or to modify it for your own research purposes. It aims to have only one dependency, which is PyTorch. But of course, it has a lot of like optional dependencies, like for your simulation environments and so on. And there are a lot of environment wrappers out there for the most popular environments used in reinforcement learning, and they're already implemented in TorchRL. Yeah, here is an overview of just some of the components, the kind of the main importance in my view. And the first one, of course, is environments. So it provides an environment interface that it's shared by all simulators. And one of the core things you see there, it's vectorized. So environments in TorchRL are vectorized by default, in the sense that every environment will have a batch size to align with this new paradigm of vectorized simulation. It provides also a set of transforms, which are basically some components that you can attach to your environment to modify its input-output. And it also comes with tensor specs, which is the equivalent of gem spaces, which are structures that just define the domain of your input-output. So they keep an eye on your data, and you can check on them to make sure that everything is within the domain and nothing cheeky is happening. Then there are some pipelines for data collection, where basically you have some classes that can do collection for you. They're similar to the PyTorch data loaders, and these have support for synchronous, asynchronous, distributed, or parallel options for collecting from your environment. It also comes with its own modules, which are basically very similar to normal Torch modules, but here we have a new functionality, which is key mapped input-output. So while in PyTorch you would normally input-output tensors. Here you can actually map to names the input-outputs of your module to make sure that, since in reinforcement learning, often there are multiple inputs and multiple outputs for a single policy, let's say, or for a single module. This is quite helpful. And these are also integrated with PyTorch components as distributions. They have their own exploration strategies, and it's also compatible with functionalities like VMAP and FuncTorch, which are aiming to be JAX-like counterparts for PyTorch. And lastly, we have objectives, which are the generic reinforcement learning losses. And here we have many of the state-of-the-art losses and support for target networks, value estimators, and so on. And what ties this all together is a new component, which is called the TensorDict. And this is something that is going to be introduced in PyTorch core in the near future. And it's basically a collection of tensors in a dictionary, which exposes an interface which is tensor-like. So this dictionary will have a batch size, for example, which will be a size that is shared by all the tensors in it. And you can see that in this case, it has a batch size of B, and this batch size is the leading shape of all the tensors contained in the dictionary. And this is actually a very useful abstraction, since reinforcement learning is such an heterogeneous domain where data comes from different places and in different shapes. So carrying it just in tensors can be quite confusing. And so TensorDict is kind of the lingua franca of this whole library. Each of these components is completely independent, and they will share TensorDicts between each other. So as long as you use TensorDict, you can use any of these components in a separate fashion. And it enables efficient, because of course it's backed by C++ code, and modularity, because it allows to separate the different interfaces for the components. And just to give an example of some on-policy simulation and learning using VMAS, what we usually do to train a multi-agent policy is that we have a sampling phase on the left, where basically your policies interact with the environment and collect tuples of interactions, which are action, state, reward data. And then all these tuples, the sensors, are passed to the training stage. And here is where basically we can benefit from the vectorization of VMAS, because these tensors will already be collected on device, on the GPU. We keep them in the batch, and we pass them in the same batch to the training loop on the same device. And in the training loop, basically, we compute the reinforcement learning loss, and we backpropagate it through the policies. And then we use the new policies for collection again, and iterate this way, improving the behavior of the agents. Okay, so now talking a little bit about multi-agent reinforcement learning. So what we had to do over the summer is design a multi-agent interface for TorchRL, or like how we can integrate multi-agent learning in the library. And this is quite a challenging task, and I wanted to just give a depiction of why. The main problem is that the multi-agent reinforcement learning ecosystem is quite heterogeneous. We can have difference in information sharing, where agents can basically share or not the rewards, the state, the termination states, the state value estimations, and so on, so leading to different paradigms. There is also quite a lot of difference in cooperation, where some multi-agent reinforcement learning paradigms can be cooperative and some non-cooperative, and this depends on a lot of things, like the incentives of the agents. There can be physical heterogeneity, where your agents are not the same, and they can have physical differences in their action spaces or observation spaces, and such their interactions might involve data with different shapes and types. Even if their agents are physically identical, they can have behavioral heterogeneity, where basically their controllers, their neural networks, can be different and represent different behaviors for the task. There is also another domain regarding asynchronicity, where agents might not all take step at the same time, but basically take turns in the task, like in turn-based games. And lastly, there is also like some differences regarding communication, where some paradigms may consider the agents sharing information in between the observation and the action in order to improve their their partial observability. So it's kind of a quite a varied background or ecosystem that we had to consider, as we did not want to like overfit to a specific solution. For example, my research would fall only in some of these categories, or maybe in a very specific case of these. So it's kind of the problem where you, when you arrive to the supermarket and you have to choose a shampoo, and there are 3,000 shampoos, and you take 30 minutes to pick one, and in the end you get conditioner. So the main two solutions that we saw here, looking at how other libraries deal with these, are these. So first, you can think of stacking the agent data. And stacking basically means that you will take data coming from different agents, and you will stack it in a new tensor, where you will have a new dimension representing the number of agents. And this will allow you to use vectorization over the agents to speed up things for computation. So here is an example where we have like agent 0 data as like camera with shape 64,64,3, and agent 1 also has a camera with the same shape. So in this case, what we can do is that we can stack these two in a new tensor, which has a new shape dimension, which is 2, represented number of agents. And this is very cool. It has some pros, and the pros are vectorization over the agents. So basically now I could potentially reuse a component for a single agent, because now the agents are in the batch dimension, and TorchRL components are agnostic of the batch dimension anyway, so I can just reuse anything I want. But on the other side, stacking cannot happen all the time. We need our data to be homogeneous, so they have to have the same shape and the same data type for this to happen. And another con is, like, if you have data in this format, usually you aim to process it with the same neural network. So it's quite more difficult to use different controllers or separate this data. On the other side, there is another possibility, which is just to carry the data in different TensorDict entries. So basically keep the data separate in the dictionary. And here we can have an example where agent 0 has a camera and agent 1 has a LiDAR. And the LiDAR, of course, has a different shape than the camera. And here, stacking would be quite impossible in traditional sense. So what we do is that we keep a different entry in the TensorDict for each of these tensors. And the pros of this is that it's compatible with more use cases, because it doesn't have any constraints. It allows heterogeneity among the data of the agents. And it's easy to use different components for different agents, because now I can say I mapped the camera key in this TensorDict, I map it to this neural network, and I map the LiDAR to another one. And I keep them separate because they require different preprocessing, for example. The cons is that we don't have any more vectorization. So we need to iterate over the agents or something when we want to process their data. And it's harder to share components across the agents. So why not both? The main thing that we saw in other libraries is that some just rely on one of these two approaches and then completely discard the other. And this is kind of a constraining approach, because what you need really depends on your needs, on the paradigm that you're considering, and on the constraints of your task. So just saying that TorchRL deals with this by stacking the agents would close a lot of opportunities for multi-agent reinforcement learning. So we let you choose what you want. And we do this via an abstraction that is called grouping. And basically, what we do is that we allow the agents to be grouped in groups that are defined, can be defined by the user. And agents within the same group will see their data stacked, and agents within different groups will have their data as different entries. And here is an example of a group map, which is basically just a structure that tells you for a group what are the agents in this group. Yeah, the cool thing about this is that once you have done your grouping for your data. Within a group, you can use any of the single agent components that are available in TorchRL. And these, for example, replay buffers, losses, or any other component, because this group will just have a new agent dimension, and those components are agnostic of that. So this is really cool, because one problem in multi-agent reinforcement learning often is that people reinvent the wheel. But while there are a lot of libraries already available from single agent reinforcement learning with some benchmark components that work. And so when you're implementing a loss that is just, for example, the derivation of a single agent loss, like a multi-agent PPO, you don't need to re-implement everything from scratch, and you can leverage some of the know-how from the single agent domain. And so just to give you 3 examples of these, how this API could work in practice, here is an example where you have all the agents in one group. So on the right, you see the balance task, which is from VMAS, and it's a task where multiple agents have to transport a package on a rod to a goal. And in this case, the agents are identical physically, and we also want them to be kind of behaviorally identical. So what we do is that we stack all the agents, and we group them in one group. In this case, it's named agents. And as you can see, this group has so the TensorDict will contain all the data, and you can see the batch size of the outer TensorDict is B. Then within the TensorDict, we will have the agents group, which is another TensorDict, which will extend the batch size. Here, in this case, you can see that the batch size of the agents TensorDict is B and number of agents. And this means that all the tensors inside of here will have this leading shape. So we'll have an agent dimension. So if, for example, if we look at the reward, it means that each agent will have a different reward entry. And you can see that out here, there is the state, which doesn't have the agent dimension, meaning that this is shared. This is the same for all agents. And you can think of a case where you don't share the reward here, where like you can just have the reward outside of the group, and this means that it will be shared by all the agents in the task. It doesn't have the multi-agent dimension. And this kind of stacking solution, it's what is used in VMAS and in the SMAC, which is a popular benchmark library. On the second case, you can think that there are tasks where some of the agents may be grouped together based on their behavior or based on their role. For example, if you think about football, you could think of grouping attackers together because maybe attackers have a certain type of sensor, a certain type of actuator, and goalies, maybe you want to group in another role. So in this case, you can define different groups, and each group will have the size of the agents inside of it. So in this case, you can see we have 2 groups. Group 1, where group 1 will have batch size B, number of agents in group 1, and all the tensor inside of here will have this leading batch size. And then group 2 with the same, where you have the number of agents in group 2. And so within the groups, the data will be stacked. And here again, you can think of sharing or not sharing the reward. It's always possible, or the downstate or anything, just by moving it 1 layer out in the TensorDict. And lastly, the last case is where you want to be completely independent among the agents. You don't want to stack anything, and you can create one group for each agent. And in this case, basically, each group won't have the agent dimension because there will be one agent inside of the group, and you will just keep the data as separate entries. And this is something that you use like in libraries like Petting Zoo. Okay, so I know that this was a lot about just training. This is a demo. We created the demo in a Colab tutorial that I suggest you to look at if you want to learning how to use multi-agent reinforcement learning in TorchRL. And basically, in this demo, we drive you step by step through how to train a multi-agent navigation scenario where different agents have to navigate to their goal while avoiding each other using LiDARs. I was hoping to actually do a live demonstration of this today, but then there was something more important that I wanted to talk about. And anyway, the tutorial is really it should be clear to understand if you want to drive through. So yeah, so the thing I wanted to talk about that I added last minute kind of to the talk is this kind of library called BenchMARL that was the product of this internship. And basically, the goal of BenchMARL is that it is a multi-agent reinforcement learning training library that it's focused on reproducibility and standardization. And this is built on top of TorchRL, so it doesn't redefine any of the reinforcement learning components. It's just links together modules of TorchRL in a way that it goes from one-line inputs to outputs that are plots and already like statistically strong evaluations that you can directly use in your papers. And basically, it has some core tenets, which focus on reproducibility, statistically strong evaluations. We want also experiment independence, where the experiment will be agnostic of what multi-agent reinforcement learning algorithm you use, or what environment you use, or what model. We want to have breadth, so support any kind of formulation when regards to algorithms, for example, of policy, on policy, actions that are discrete, continuous. We want to abstract over all these. We want it to be easily integrated so that you can implement your own algorithm and compare against the ones that are already available or the environments already available. And one of the most important things is that it has a TorchRL backbone. So all the important reinforcement learning components are maintained in TorchRL, and they have all the guarantees that TorchRL has without needing like extra reimplementation in BenchMARL. And just a brief message on why this exists. The main problem that reinforcement learning has kind of always had is that it's quite fragmented when it comes to standards of the community with respect to other supervised or machine learning domains. And this has recently been highlighted in NeurIPS in 2 papers that highlight this reproducibility crisis. And these papers propose a set of tools for reporting results. And you can see on the right some of the statistically strong tools and plots that they suggest. And so BenchMARL kind of provides the infrastructure to generate these plots and these tools and to just try to uniform all the benchmarking process. So it hooks into these tools provided. One of them is by InstaDeep, the other one is by Google. It just hooks so that you can use these kind of plots. And okay, this is just there's a lot of things for one slide, but it's just an overview of the components and the different things that are available inside. But basically, launching experiments and benchmarks is very simple. For experiments, you just need to say what algorithm and what task you want to use. And for benchmarks, you can just give it a list of algorithms, a list of tasks, and it will run each pairing. And you can choose the backend to be parallel, sequential. You can even choose SLARM backend to make it easy to send this to HPC cluster. And yeah, on the algorithm and the task side, I want to go into that today, but as you can see, there are many different types of algorithms that are on policy, actor critic, full observability in the critic, different action spaces, different if the actor is probabilistic or not, and also some tasks from different libraries such as SMAC, which is very popular, VMAS, and others. Yeah, and as the last thing I want to say, just an overview of the other features that BenchMARL puts available is the configuration is basically standardized using YAML, and we use a project from Facebook called Hydra, which is a really cool project to standardize your configuration of your machine learning applications. And it's very easy to override this YAML configuration from the command line. It also supports logging with the most famous things like 1DB and so on, checkpointing, callbacks. We have tests with the CI it's constantly run on all algos and environments with integration tests. And the last thing, the most important for me, is that what we aim to do is to publish these benchmarks online. You can find here a QR code to the 1DB notebooks, but basically for each environment, what we want to do is to make publicly available the plots generated by benchmarking this environment with a set of hyperparameters that have been tuned. And at this link, you will be able to find the interactive 1DB plots as well as the static plots that you can use, that you use in the papers usually, to just see the difference and interact with the data. Yeah, and this was everything that I wanted to touch upon today. I wanted to make a special thanks to Vincent Moyes, which is the maintainer of TorchRL and was my supervisor during the internship. And this is all possible thanks to him and all the support that he gave and in the library. And then, of course, a big thanks to Amanda Prorok, which has been supervising me for my PhD throughout all these years, so for all these projects. And to get involved, if you're interested in any of these, you can reach out or join the discussions on GitHub. We are always looking for contributors on any of these projects. Here are the links to the GitHub repos. Yeah, and thank you very much.